Hi folks, this is Maria. In this video, we're going to talk about light diffraction and light scattering for particle size A. So this map that you're looking at is basically how I store and understand this whole set of knowledge in my brain. It might seem to be a bit messy for some people and oversimplified for others, but let's just give it a shot. I'm sure I can make you understand as well. So let's start with the first column here, instruments. We have masterizers and zetizers. They are corresponding with the rest of the roles here, basically, that I will talk about later. So instruments are based on the technologies, and technologies are basically names we gave to the theories we apply to this type of application. So what are theories? To my point of view, theories are basically the rules we summarized from the phenomenon that we observe, and or I would say mathematical equations we summarize from a set of similar experiences so that we can use these rules and mathematical equations to solve other experiences and solve problems, basically. So that's theories and phenomenon. And behind all this, that's the essence. I think there's the word called essentialism. That's off topic. So the essence is really like my way to study for things. So since middle school, so whatever I am studying for, I will try to find out the essence behind it. Once I understand the essence, I can understand the rest of things relatively easier, like a lot easier. So I think the essence behind all this is to understand light. Okay, so let's start here. Um, how to understand light? So I didn't put what's light because we were told that light is both wave and particle. This sentence sounds pretty smart, but it can be confusing too. It's really how we understand it. So really, how do we understand anything? We understand new things based on the things that we've already understood. Um, in this case, we've already understood a wave, like a mechanical wave, like water wave, and like a rope that you can just swing. So that's wave is something we understand and we experience every day in our macroscopic world. So we summarize the rules for waves and we use it to solve the rest. So we found out that light just behave similarly to the mechanical waves we observe every day. So that's why we can understand light based on our understanding of waves. And also, we observed that light follows the same principle for of particles. So the word particle, I would like to comment here, is used not too much, but like really a lot. Like particle can be graviton, like quantum particles, and the particle can be a ball that my son can play with. So what is a particle really? So I think we call a particle because it follows the rules that a little ball follows. We can have a ball here and do some simple experiment to figure out its momentum, velocity, acceleration, mass, and this whole set of rules describe a particle. So anything that follows this type of rules or mathematical equations, we call them a particle. So that's my understanding. Okay, for the scope of this presentation, it's better if we understand light as a wave. So let's talk more about waves. There are two types of waves. First is mechanical wave. One example is this, as you can see in this picture, is we can call it a people wave. So basically, each individual sit at their own spot and moving up and down, up and down, up and down, and they can be holding hands. So my movement influence yours. You are moving up and down too, at a different time point, of course, and the whole movement propagates through the direction of this wave, but each individual stays at their own spot. So there are 2 points I want to make on mechanical wave. The first point is that each person, or in other cases, each molecule, they stay at their own spot, moving up and down. And this rhythm of movement propagate through the direction of the wave. So the second point is the mechanical wave is the motion of the medium. So it definitely requires medium because the motion of the medium is the mechanical wave itself. Okay, so that's mechanical wave. So what is light then? Light is not a mechanical wave because light doesn't need medium to travel. It travels in vacuum in a space. So what is it? It's a electromagnetic wave. We call it a wave because it behaves the same way as a mechanical wave in terms of, I guess, mathematical equations, all right? So what is electromagnetic wave? So it's really, I think, it's oscillating electromagnetic fields, like similarly to a mechanical wave at each spot. This field is oscillating up and down, up and down, up and down. So take home point here is that light is an electromagnetic wave, which is an oscillating electromagnetic field at each point of this wave. Okay, I hope that make it clear. So one comment I would like to make is that the how this wave travel is really like one spot influence the next spot that's next to me. Like for people wave, either we are like we planned to do this, or like we are holding hands, so my movement influence yours. For electromagnetic field, the field at this spot influence the field at the next spot. So that's how the wave is traveling. At least that's my understanding. Okay, now we understand light is an electromagnetic wave. We can go ahead and talk about the phenomenon that we observe or with regard to light. So the first phenomenon is diffraction. So forget about light diffraction, just diffraction itself. What is diffraction? Like think about it in terms of a mechanical wave. Really, diffraction is wave superposition. What I mean by wave superposition, we've all learned it in schools. So if we look at this graph here, the wave at this point, if this is the like high point of this wave, the highest point of this wave, and if this point over here is should be the lowest point of this wave, then it cancelled out so that it appears in the diffraction pattern that this spot is a black spot. So that is wave superposition, and we observe it in mechanical waves like a water wave, also in light waves as well. As you can see here, light passing through particles, and we observe some patterns just like the mechanical wave. And I would like to comment here that light passing through a particle, an opaque particle, meaning a particle, the light wouldn't propagate through this particle. So light passing through an opaque particle equals to the negative of light passing through a single slit. And this point is very important because that's how mathematically we derive equations to calculate the particle size from the diffraction pattern. Okay, so that's diffraction. Take-home point is that diffraction really is wave superposition. Okay, so that's diffraction. Now let's move on to the next phenomenon, which is light scattering. So light scattering is the opposite of diffraction in terms of that the particle needs to be optically soft, meaning the light needs to propagate through this matter and get out. So let's start light scattering with a video that I wanted to show you. Okay, so here is an incident light. As you can see, the light get inside this particle and have some interactions with the particle that I will introduce later and get out, of course, at different angles. And actually, you can just understand this color as an energy because basically everything is energy, and this energy in this case is electromagnetic field. Okay, that's basically it. Okay, I will start introducing this idea of light scattering from matter and electron cloud. So what is an electron cloud? Let's start from an atom. We all know atom in the center, it has protons and neutrons, and outside the center, if it got electrons, which are negative charges that orbit the center. And at each point of the orbits, the electron exists in the form of a probability. So basically, the density of an electron cloud at each point is a probability. So that's the basic idea of an electron cloud. And let's move on to a molecule, like a water molecule, because now it forms a molecule. The electrons arrange themselves to form a new electron cloud, and we call this the electron cloud of a water molecule. The same idea applies to a bigger molecule like a protein or like any bigger molecule that you can think of. And basically, it describes the electrons inside this molecule and its arrangement. Okay, so that's electron cloud. So what happens when a light passes through an electron cloud then? That's the next point I want to make. An oscillating dipole is generated. So yes, as I told you, light is a electromagnetic field. When an external field being exerted on an electron cloud, and this electron cloud has the freedom to arrange its negative charge a little bit to adjust to this external field. So the goal is to stay neutral. That's what we like, right? So once you exert a positive field on the electron cloud want to create a negative one that cancels this out so that the whole thing stays neutral, right? So whatever the external field is, the electron cloud generates an internal field to cancel it out. So the internal oscillating electromagnetic field generated by the electron cloud is then what we call the scattered light, because an oscillating electromagnetic field is the light itself. And the next point I would like to make is that this internally generated oscillating electromagnetic field is oscillating at the same frequency of the incident light. Why? Because this internally generated field is created due to the external field, and it wants to cancel it out. So it has to oscillating at the same frequency. I think the idea is pretty clear. Okay. Okay, so that's light scattering. Okay, I think that's enough for this video. Let's cover the rest in the next video. And thanks. Bye-bye.